Hey everybody, welcome back to another round of physics, and yeah, let's get going. The idea that I wanted to present in this video is the idea of vector fields. Now these are mathematical concepts that we'll find useful both in this class but also in future engineering science courses in general. So in the context of this class, the issue is that we have described the interaction between charges using the Coulomb force. What we haven't discussed and what we haven't set the foundations for is how to conceptualize the interaction between charges when they're not touching each other. This same conceptualization also can be applied towards the gravitational force, any force where there's an action at a distance. We don't like that idea that there's some sort of underlying physical entity that connects the particles together. And so that's what we're going to start developing and starting to talk about. So this is the question: how do charges know about each other? Okay? So I thought, well, first off, we'll start off with a little video of trying to figure out or measure a vector field. And I'll just let it play and talk over it while we're going. So you notice I have an overhead view of a sheet, and I have some ball bearings in my hand. And the idea here is that, can I use those ball bearings to create a velocity vector field? So you notice I'm dropping them at different locations. And again, okay? And you notice that as I release the ball bearings, they're going in different directions. They're going at different velocities at different points in time. And ideally, we could spread a whole bunch of test particles all over the place. And if we measure each of those test particles, we can get a sense of the velocity vector field. Now, I've taken a screenshot of just simply one, and let me walk you through. I took a handful of ball bearings. I dropped them at a single spot right here at the center at the same time. So I just, let go. So you could imagine for a second how we could get an idea about the velocity vector field just using some of these particles. Well, first off, notice since I dropped them all at the same time, okay, and at the same location, you could say the distance to each of those marbles is indicative of how fast the marble is moving at the instant that I took that picture. Right? So marbles that are closer to the starting location must have been moving slower. And so when I'm creating an arrow to represent the velocity of that marble, I better draw those arrows smaller. So I've just put 3 in there. Those are roughly the same distance away from the starting location. Now, marbles that are slightly further away, say, I don't know, this one, that one, this one, since they're further away, they're clearly moving faster, and therefore I should put arrows that are slightly longer. And of course, you have a couple marbles that have gotten really far away from the starting point. And so I can even do larger marbles that way. Now you can imagine for a second, pretend that I got rid of the underlying image. These arrows would represent a vector field for the velocity. Now, of course, you say, Greg, I want to have finer measurements. I want to do, better measurements of it. Well, that's fine. Take a handful of marbles, more marbles, drop them on the center, and take another picture, and you can start building up an idea about the vector field for the velocity. Now, of course, that's a little contrived example, just set it up in the office, but you've dealt with these things before. So, for example, one of the things I'm thinking about, it was particularly windy outside yesterday, and one of the things I'm thinking about is, well, that is another way that we represent wind speed. Namely, our measurement device is not marbles that we're dropping all over the place, but rather our measurement device is, I have no idea what this is officially called now that I think about it, but it's a wind gauge, right? And remind yourself you need two pieces of information in order to form a vector in the first place. You need a magnitude and you need a direction. If we look at this device, you can see where we would record both of those. On the right hand here is, I guess best termed, like a weather vane. So when the wind blows, it pushes the tail, and the weather vane aligns with the direction the wind is blowing. And if we put a little encoder or some sort of measurement device to measure the rotation angle in the base, now all of a sudden we have an idea about which way the wind's blowing. What we don't have yet is how fast the wind is blowing. And we can see that's what this device is for over here. And so when the wind blows, it spins the whatchamadoobab, or the pinwheel. I know that's not the official term, but it's a windmill or a pinwheel. So when the wind blows, and there's again a little measurement device in here, some sort of a encoder to record the angular speed of that device. And based on the angular speed of that device, presumably everything else, all the other physical quantities that might be necessary are known. And then you can get a wind speed there. So the combination of both of those measurements give you the velocity vector for the wind. So what's the last thing that we have to do? Let's put these stations all over the place. Like all over the continental United States, or even better, all over the entire world. And what we can then produce with each of those data measurements, we can produce a vector map that's giving us an idea about wind speed. Okay? Now, there's some questions that I should ask you about this. Rhetorical questions, but these are good things to be thinking about. So the first thing I should say is, you notice Hanover, Indiana, I'll say is right here. Okay? That's a little off, but yeah. Okay. The question, okay? Even though there's no arrow there, right? I've circled a region that doesn't have an arrow. Does that mean the wind is not blowing in Hanover? No, of course not. That's one of the things to keep in mind when we present a vector map like this, is that even though there is not arrows drawn at every single location, you can extrapolate in your mind between drawn arrows to get a sense of the wind at other locations. So for example, right here we see that there's an arrow going that way, there's an arrow going that way. So in between those two, you would imagine there must be some sort of arrow wind speed going down. Okay? Even though the arrow is not drawn there. Okay? And you can see that's done for a practical reason. If I put arrows at every single location on this map, then the whole map would just be arrows. It would obscure everything. So that's one important piece to remember, is that when we do these vector maps, or when we want to draw these vector fields, we want to draw enough vectors to get a sense of what's going on without actually obscuring everything and wasting ink and all that kind of stuff. Okay? Oh. Now, the other thing that's always interesting here is that wind, for example, when we're dealing with weather patterns, wind tends to blow from high pressure regions to low pressure regions. Okay. So another question I have for you, you can pause the video here and just work it out, but based on this vector map, where are the high regions and where are the low pressure regions? Yeah, good. So you can say, well, if wind blows from high pressure to low pressure, if we find locations where arrows are all, the technical term is diverging, going away from each other, if we can find those particular locations, those must be regions of high pressure. So we start looking around and we say, okay, well, down here in the Antarctic, it seems like all the wind's just going in one particular direction. Now we start hunting around, and we see right here over, I guess this would be like central Brazil, you can see that there's a high pressure region. I'll put a big H here. And how we know that is because all of the vectors are going away from that region. So that must be a high pressure region. Well, where else? Oh, it looks like we have one in northern Australia. I guess that might be Indonesia. Okay, so there's another high pressure region. We see we have another high pressure region over something like Madagascar. And maybe even one, might be able to find one maybe over here in northern Russia, but it's not particularly large. It's not a strong high pressure region because you notice that the wind, although it might be diverging, you can see that the vectors are a lot shorter. Okay, so it's a gentle breeze rather than, a strong gusty 35 mile an hour kind of thing. Okay? Now conversely, we can get an idea about where the low pressure regions are. If high pressure regions are regions where the vectors diverge, low pressure regions will be places where the vectors converge, they come together. And again, we can start going around and looking, but we're looking for places where the arrows come together. And right away we see that, I don't know, I guess we'll call this Montana, Colorado, something like that. But we see in the central United States, there's an area where the arrows are coming together. Where else? Oh yeah, northern Africa, so Algeria or Tunisia, somewhere around there, there's another low pressure region. And even right here, you notice that somewhere in the Pacific Ocean, it looks like there's another low pressure region right about there, et cetera, et cetera, et cetera. And you can play this kind of game. Now, we'll keep that in mind. Even going back to the example with the video, you could say, well, the marbles are going to roll not from high pressure regions to low pressure regions, but the marbles that we had are rolling downhill. So they're going from places of high elevation to places of low elevation. And that's how, that's why they diverge from the peak and they go towards the trough. We'll keep that idea in mind. Traditionally, vector maps have arrows drawn. Of course, we talked about magnitude and direction. This animation here, it's a different way of conveying the same sort of information, where the color scale is kind of giving you a sense of the high and low pressure regions. And of course, the animation itself shows you the wind speed and the direction all in one. Now let's bring it back to our idea about charges. Okay? We've already talked about Coulomb's law, and here's how we're going to think about it. We would like to create let's say a vector field or a vector map, thinking about the forces due to this central charge, capital Q. Okay. So what will I do? Well, in the case of wind, we put that little weather vane and the little speed thingamadoodad. In the case of that sheet that I had for the video, it's the marbles. And for the case of Coulomb's law, what we do is we drop what we call test particles, just like those little marbles. Okay? And what we would do is we would take this test particle, which is always positive, by the way, and think about dropping it in the vicinity of this charge, capital Q. Now, we already know, first of all, if the test particle is positively charged and Q is positively charged, which direction will the force on the test particle be due to Q? And this is our surroundings now, and this one is my system. Yeah, you say, of course, I know it. Like charges repel, and so my system will experience a force that forces it away from the surrounding particle. Well, what happens if I drop a test particle on the left-hand side? Say, I know that. It's going to go away. So in this particular case, it should go to the left. Well, how about if I put one in, the 5 o'clock position? Same idea. Okay? And in fact, you could imagine sprinkling those test charges all over the place. And as I sprinkle them down, I get a sense of the direction that the force experienced by our test particle. Okay? And so we're slowly building up a vector field indicating the force on our test charge due to this central charge Q. Well, last one, what happens if I thinking about this distance for a moment, what happens if I double that distance? In other words, if I drop the test charge twice as far away. Yeah, think about the forces for a second. What happens to the magnitude of the Coulomb force if you double the distance between the charges? Yeah, good. You remember Coulomb's law is an inverse squared relationship. The force is inversely proportional to 1 over the distance squared. Okay? So if I double the distance, the force experienced on this test particle due to that charge should be decreased by 1/4. So I should draw my vector field smaller. I should draw the arrow smaller. And again, you could do the same thing. You say, well, what happens if it's over here? I should draw it smaller, and specifically it's 1/4 the size. So I'll draw those in. Well, what happens if I get even further away? Say I do 3 times the distance. Well, you say, okay, well now it's 1/9 the original arrow. And so 1/9, and I won't belabor the point, but you can get a sense of how that vector field, how the magnitude decreases as you move further and further away. Okay, good. Now, the other question I should ask you, if I want to make an analogy with geography, which I find myself, I like thinking about geographical features and kind of making analogies there. So the question I have for you here is, would this situation, would this be better represented as a hill or a valley if I'm thinking about kind of like geological features and dropping physical, marbles all over the place to map out my vector field? Yeah, good. Well, you notice that all of the test charges are going away from that central area. So if I had a valley and I dropped a bunch of marbles on the valley, would they actually move away from the center? You go, no, of course they would collapse towards it, okay? Well, how about a hill? Well, yeah, if I put a bunch of marbles on top of a hill, they're all gonna spread out. We'll come back to that idea very quickly, particularly when we're dealing with something called the electric potential. Okay? So, yeah, in fact, there we go, you got a hill. You can think of having this background as a hill. Okay, so I think I will leave it there for right now, but we're going to start getting into this idea about vector fields. And in particular, we're not going to be talking about forces, we're not going to be talking about velocities. Rather, we're going to be talking about a very specific type of field that we introduce in physics called the electric field. So hopefully you're ready for that. In the meantime, I thank you for your attention. Keep up the good work. I'll see you next time.